Imagine a sleek electric car gliding silently down the road. Hidden beneath it is a battery pack, thousands of lithium-ion cells, each powered by a dance of atoms. In every discharge cycle, lithium atoms in the graphite anode lose an electron and become Li+ ions. These lithium ions slip through the electrolyte separator to the cathode, where they pick up electrons and neutralize. It's this shuttling of Li+ that powers your phone, laptop, and EV. Because lithium is extremely light, the third smallest atom, a lithium-ion cell can store a massive amount of charge per weight. No wonder lithium-ion batteries dominate. They account for 80% of the nearly 190 gigawatt-hours of global battery storage installed through 2023, powering everything from smartphones to Tesla Model S sedans and electric 787 jets. Deep inside each cell, a cathode and anode hold lithium. Early lithium-ion batteries used a lithium cobalt oxide cathode and a layered graphite anode. Graphite's carbon sheets open like pages to intercalate or insert Li+ ions between them. When charging, lithium ions are forced back into the anode. When discharging, they leap out and travel to the cathode, releasing energy. This intercalation is highly reversible, giving lithium-ion cells long life. And because lithium ions are so small, today's cells reach exceptionally high energy densities, up to about 330 watt-hours per kilogram, far above old lead acid, which is around 75 watt-hours per kilogram. Think of a single kilogram of lithium-ion battery as a small brick, about the weight of a laptop. That tiny brick can power an electric car for over 2 kilometers, or run your smartphone non-stop for 4 entire days. Stack just 300 of these bricks, and you've got a battery pack that can drive your EV from New York to Toronto without recharging. But even lithium-ion has limits. To fully power a renewable grid, we need terawatt-hours of storage, roughly 100 times X of today's deployment. Scaling lithium-ion that much would stress supplies of lithium, cobalt, and nickel, and require batteries to drop below $100 per kilowatt-hour. In short, the coming energy revolution needs even more advanced batteries, and that means looking even deeper at the level of atoms. What if the anode weren't graphite, but silicon? A single silicon atom can bind 3.75 lithium atoms, forming Li 3.75 Si, compared to just 1 Li per 6 carbon atoms in graphite. That gives silicon astronomical theoretical capacity, nearly 3,579 milliamp-hours per gram, nearly 10 times graphite's around 372 milliamp-hours per gram. In practice, adding silicon nanoparticles to graphite can boost a cell's capacity dramatically, promising smaller, lighter batteries. There's a catch. Silicon expands. When fully lithiated, it swells by about 300%, cracking like a shaken concrete block. Each charge cycle pulverizes the silicon and breaks the protective SEI layer, slowly killing the battery. Engineers are fighting back, for example, using silicon nanostructures or silicon graphite blends to absorb the stress. But the volume change puzzle makes pure silicon anodes an ongoing research challenge. Now imagine removing all the liquids in a battery cell. Toyota's lab has prototyped an all-solid-state battery using ceramic or polymer electrolytes instead of flammable liquids. This simple switch is revolutionary. Without liquid to ignite, safety dramatically improves. Solid electrolytes also allow the use of a lithium metal anode instead of graphite, since the solid barrier can block dendrite shorts. In other words, you can pack much more lithium into each cell. Research shows solid-state cells can be far more energy-dense and durable. They're lighter and don't need heavy cooling systems. For example, major battery labs report startling stats. China's CAT is trialing 20 amp-hour solid cells at about 500 watt-hours per kilogram, 40% better than today's top lithium-ion. Samsung claims its pilot solid packs will enable 600-mile EVs that charge in 9 to 10 minutes. A VW QuantumState partnership is aiming at 80 gigawatt-hours per year of all solid-state cells, enough for 1 million EVs per year. In lab tests, QuantumScape's own new solid-state cell, QSE-5, reached nearly 844 watt-hours per liter and charged from 10% to 80% in about 12 minutes. That's equivalent to a full charge in the time it takes to drink a coffee. It also demonstrated nearly 95% capacity after 1,000 cycles. Solid-state batteries promise higher energy density and zero fire risk, a true leap forward. What about cathodes? One radical idea replaces metal oxides with sulfur. Lithium-sulfur (LiS) batteries use a lithium metal anode and a sulfur-carbon cathode, theoretically reaching 2,600 watt-hours per kilogram, more than twice today's lithium-ion. Sulfur is abundant and cheap, think of it as nature's free cathode material, but it's not easy to harness in a rechargeable cell. Still, progress is striking. For instance, a startup called LIS Energy built a 10Ah semi-solid LIS cell, achieving approximately 498 watt-hours per kilogram on first discharge. Another player, Lithium, has raised $1 billion to build a 10 gigawatt-hour per year LIS Gigafactory, full production by approximately 2027. Stellantis, Daimler, and Zeta Energy are developing LIS packs aiming for 50% faster charging at half the cost of lithium-ion. Lithium even bought Northvolt's technology from bankruptcy. And a recent Nature review reminds us LIS can be twice as energy dense as lithium-ion while using no cobalt or nickel, all huge advantages if the cycle life puzzle is solved. Not all batteries need lithium. Sodium-ion, Na-ion batteries work on the same principle, Na+ shuttles instead of Li+, but use cheap, abundant sodium. Sodium is heavier, so energy density is lower, but it is non-flammable and extremely cheap. In 2024, CATL launched a new sodium-ion line, brand named Naxtra, with 175 watt-hours per kilogram energy, already comparable to typical LFP cells. Experts note sodium-ion cells can endure many more cycles, up to 50,000 cycles, 5 to 10 times lithium-ion. Next-generation sodium-ion, Cattler's second gen, is expected to exceed 200 watt-hours per kilogram, which would be a major milestone. Meanwhile, BYD and others are building 10 to 30 gigawatt-hour sodium-ion plants. Other chemistries are also in play. Flow batteries, like vanadium or iron flow, decouple power and energy and are promising for very large-scale grid storage, though they are bulky. Zinc-based batteries, Zinc Air, Zinc Ion, offer high theoretical energy, safety, and recyclability. For example, Zinc Air, as in hearing aid batteries, uses oxygen from air and zinc metal, giving huge capacity. The trick is making it fully rechargeable. All these alternatives aim to reduce reliance on scarce materials and tailor batteries to specific needs: fast grid pulses, long-term storage, cheap rural power, etc. The science is advancing fast, and factories are racing to catch up. China still makes 85% of the world's cells, but investments are booming globally. Startup gigafactories like Northvolt, Freer, and companies like Tesla, LG Chem, and Cattler are building dozens of lines. Automakers are placing 10-year bets. Volkswagen, GM, and Ford have announced new battery plants with joint venture partners. Meanwhile, VC dollars are pouring in. Over $1 billion in late 2023 to solid power, another $1 billion to StoreDot, fast-charging batteries, and so on. These all recognize the next revolution is not just in the lab,
but in gigawatt-scale manufacturing. At the same time, recycling will close the loop on the hidden atoms. J.B. Straubel's Redwood Materials, founded by Tesla's ex-CTO, exemplifies this effort. Redwood says it can recover greater than 95% of lithium, cobalt, nickel, and copper from old EV batteries. In 2024 alone, Redwood recycled 20 gigawatt-hours of batteries, enough for 250,000 new EVs, sending those atoms straight into the supply chain. Other innovators, like Li-Cycle, Umicore, and Recyclico, report similar breakthroughs in hydrometallurgical and even direct recycling. The result? The raw materials in every phone and car battery of tomorrow can largely be reused, alleviating mining pressure and emission footprints. The energy revolution in your hands. This is a story of atoms and of people. Each new battery material or design is a chapter in the energy revolution. When you plug in your EV, charge your laptop, or store solar power at home, remember, science has been rewriting what those little lithium or sodium atoms can do. The future is bright. Safer solid electrolytes, ultra-high energy anodes, and even batteries that last 5 times longer. We're literally engineering energy at the atomic level to tackle climate change, air pollution, and the limits of today's tech. And the best part? Anyone can join in. Consumers voting with green choices, engineers innovating smarter cells, investors funding the next startup, government supporting clean energy. Every action helps steer this revolution. The atoms are waiting to be disturbed. The innovations are here. Our challenge is to harness them. Let's power the future, one atom at a time.